All right. I have some homeworks. Um, it- was anyone expecting a homework and didn't get one back? Did you?
Yeah, you
I-
sent it in, and then it was a rock file, not as a file. He's going to resend it, so I sent it back on Sunday.
Okay, I haven't graded it yet then. This is just stuff that's I printed out the day after I collected it. So I'll get yours back as soon as possible. Any questions on assignments 1 or 2? Yes.
Are they going to be used for assignment 3 as well? Like connect to that?
Yes. Every assignment in this class will build on the previous assignments. So I strongly recommend, if you got points off on one of these assignments, come see me. Make sure you figure out what went wrong on those assignments, so that you can start out without having to worry about any errors from previous assignments affecting things from future assignments. I won't take off points for the same thing twice. So as long as everything compiles and doesn't crash when it's run, I will take that into account if I don't see the output that I'm expecting. If it's something that was incorrect from a previous assignment, I'll just gloss over it, won't even worry about it. I'm only focused on things that are specifically for the specific assignment that I'm grading. I'm pretty sure that it would be difficult for me to post a compiled version of the program like I did for instruction, because I'm pretty sure that toward the end of the semester we have to change something. We have to add to program. Unfortunately, Java doesn't have something called partial classes, so I can't build half the class and have you build the other half of the class. Machine, which is what you're writing for Thursday, definitely will be built on in successive programming assignments. So each programming assignment, you'll end up adding a few methods to machine. The bulk of it is written for this assignment, and this is where we write the bulk of the interpreter. So at the end of this assignment, you have most of an interpreter written, which will be pretty cool. And then we add on the ability to execute certain instructions as we go to show the use of different data structures. At this point, assignments 1 through, well, obviously 1 and 2 and 3, but 4 through 6 are posted. I edited them. They make sense. The implementations should actually work, and there shouldn't be too many questions. programming assignment 7 hasn't quite been written yet, so I'll obviously post that before we actually have to do it. Speaking of writing things, I wrote an exam over the weekend. We have an exam next class. It's my birthday present to you guys. It is my birthday on Thursday, so I'm giving you an exam. Not my intent. That's just the way the days worked out. So, right, it covers all material up to and including this class. So again, if you have questions on that, make sure to see me before the exam. I won't actually pull the exam up on the screen, but let's see. My computer's gotten kind of goofy. There we go. So the exam is Thursday. It is open book, closed notes. It is completely short answer. By short answer, I mean 4 sentences or so per question. So it's kind of open-ended, so one of the instructions is state any assumptions that you make. It's okay if you think in a different direction than I do, as long as you specifically say, this is how I understood the question. I don't want to take off points even if you know the right answer just because you interpreted the question differently. I want to give you points. That's the point of a test. It's to give you points. Despite what other instructors might say, the point of a test is to give you points. It's divided into, 4 parts, I think. Each is worth approximately 50 points. Part 1 is background. Sorts of things to know for that section are things like, in general, what the point of data structures are. Why are you taking this class? Aside from the I need it for my major. But what's the point of this class? What's the overall goal? Basically, hopefully I covered that in the very first class. Some of the other background is more general Java concepts like object-oriented programming and overview things that are necessary to tie into data structures, but not specifically new material in this class. All stuff that I did talk about, though. The iterable and iterator interfaces, it's a good idea to know why they exist, how you might use them, and the basic idea of Chapter 5 on generics. So I think that's 4 chapters knocked out of the way right off the bat. And then the other 3 parts look specifically at the 3 data structures covered in the other 3 chapters. Linked lists, stacks, and queues. A very big, important thing to know about each of them is what they are, how they work, what their reason for existing is, and preferably be able to draw a picture of them. Each one has a pretty standard picture, or at least you should be able to draw something that resembles how each of them function. And then the other questions in each of those sections are describing the mechanics. So how you would add elements to a linked list or a queue or a stack. How you remove elements, what you can and can't do with them. Let's see. In chapter 6, I think it is, on stacks, the author gives two implementations of a stack, one with arrays and one with a linked list. We did the linked list example in class because it's a lot simpler to code. It's absolutely trivial to code. The array implementation, not so much. You should be able to give a couple sentences describing why we did the linked list stack in class and what benefits the array linked list might have and why there are differences. Make sure you understand the idea of stack-based math that you're implementing for this programming assignment. And the idea behind postfix notation and what that means in terms of what's called infix notation, the way we usually write our math. And the final question on the exam has to do with a specific piece of the implementation of a queue, which we're going to do in class today. And I will actually answer the last question in class today. And the answer to that question is also in the book. That's as much as I'm going to tell you about that last question. Overall, the exam is worth 200 points. The most that any question is worth on the exam is 20 points, I think. There are 13 questions total. Yeah, that makes sense. Ranging between 10 points and 15 points. So no one question is a large portion of the exam. So I would definitely recommend focusing on the questions that you know the answers to first, and then going back and writing something for the other questions. I definitely recommend writing at least something for each question. It is very difficult for me to give points for a blank answer. No, it is impossible for me to give points for a blank answer. If you write something, I can at least try to give you points, even if you don't know the right answer. All of these questions should evoke some thought process, though. If you've been paying attention in class and reading along in the book, which all of you have, I saw that smirk. Okay, so maybe not one of those two, but those that don't have the book I recommend getting the book or memorizing it before the exam. If you've been paying attention in class at least, all of these questions should evoke some thought, and whatever comes into your mind immediately after reading the question probably has something to do with the right answer. That's the way I take exams most of the time. I look at the question and whatever I think of first, that goes on the paper. Any questions about? Yes.
Would it be anything like we have to write code? Like, will you ask us how to do this?
Get his pseudocode. Let me. Yes, closest you get is pseudocode. I don't expect you to be able to write Java onto a piece of paper, though that would be impressive. If I'm not going to compile it, why go the extra step and say it must be syntactically correct.
Well, that's how my Java class, those are my exams, and I had to write full codes by hand.
I have had to as well.
Yeah.
I have taken exams where I had to write a full Java program on a piece of paper. It was never going to compile, but the instructor was that pedantic that if you missed a semicolon, you got points off. Not me. I am more interested in concepts, and this class, particularly this class, is very much a concepts class. All of these data structures, they're not specific to Java. You can implement them in any language you want. Java just happens to be the language that the university chooses. And by the way, that's the reason that you have to learn Java in the intro class. Java is an absolutely terrible language for an intro language. The only reason you learn Java in the intro language, in the intro class anymore, originally was because Sun really liked education and just dumped a whole bunch of money and resources into education. So Java was one of those things. Sun's no longer around. They're part of Oracle now. But Java is a great language because of its object-oriented nature for data structures. And in order to use Java for data structures, you have to know Java. In order to know Java, you have to have learned Java somehow. So they use that. Basically, in the intro class, kill two birds with one stone. Learn basic computer science and programming concepts, and learn how to write Java. One of those goals is more painful than the other, far more painful than the other. But that's the way things go. Any other questions on the midterm? Cool. With that, let's talk about queues. I was going to use the iPad, but that was what was crashing my computer, so we're not going to do that. So, queues. Let's take a step back from computer science for a second. What is a queue? Sure.
Isn't it kind of like a stack, like it comes down and it's that like the stack goes back and
That was less computer science. So we've all stood in the line at the Overlook. In England, they call those queues, and probably in other parts of the world. So if you're talking to someone who's from England and they talk about waiting in a queue, they're talking about waiting in a line. It's just as irritating. It's just a different name. So in computer science, queues work exactly the same way as queues lines that you stand in waiting for food. Nasty, overpriced food. So, like you said, it is first in, first out. Stacks are first in, last out. So, with stacks, you put things into the top, and now's when I really wish I could draw pictures. Stacks, you put things in the top, and you take things off the top. Queues, you put things in, usually we turn that model on its side. You stick things in one end and pull things off the other end. Though the operations are still called the same thing. I think the book uses those same terms. Push and pop and peek. Stack, queues. So the example the book uses to start off with is the idea of a car wash. I use the example of a lunch line. Same difference. Same thing. Come on. Where is it? Add. So it looks like the book. Oh, here we go. Right. All the way on page 399, which I don't know why it ends up here. There's a table that shows you can just look at the front end column because that actually talks about a double-ended queue, which gets kind of confusing. You can have a queue going both ways. So people are leaving the overlook because they don't want to wait in line anymore, and people are continuing to move towards the food getting area. But the main operations are push and pop. Push puts an element into the tail end, I suppose. When it comes to queues, we start talking about fronts and rears. So the front is where kind of arbitrarily chosen to be the people closest to getting food. I'll stick with this overlook analogy. And the rear, the back of the line, are the people who are going to be waiting for the next half hour to get food. When we push something onto a queue, that adds one more person to the end of the line. When we pop something, that means someone got their food and they're now waiting in another queue over by the cash register. To go with the car wash example, as I drive up to get my car washed, pay my $5 or whatever, I am being pushed onto the queue. After I go through the car wash, I am popped off the queue. Everything else is identical to all the other data structures that we've looked at, linked lists and stacks. The size is the number of elements in the queue. We still have the peak, which means figure out who's next on the queue, who's frustratedly waiting for their food, but not actually give them their food yet and pop them off the queue. Let's see. What else can we say there? And just like with stacks, we can implement a queue on top of a linked list. We have a head and a tail of a linked list. We can probably choose the head to be the front of the queue and the tail of the linked list to be the rear of the queue. Keep the terms kind of synonymous. And in that case, popping something off of the queue would just be a matter of basically removing the first element. Moving head to point to the head elements next. Popping something onto the queue would be looking at tail, setting its next to a new element, and changing tail to point to that new element. But the book uses something called a circular array, which is kind of interesting. And it's probably the most efficient use of space that you could possibly use. It does require some extra overhead for adding, removing, pushing, and popping. And it presents sort of a problem. Well, arrays by themselves present a problem. Let's say I have an array of size 10. I push 8 elements on. I pop 4 of them. It really doesn't matter how many. I push 2 more elements on at the end. If my pop operation doesn't change the location of any of the elements in the array, now I have 4 elements because I popped 4. 4 elements at the beginning of the array that aren't being used, and the remaining 6 elements in the array are being used. I'm at the end. What do I do? One option is to increase the size of my array, the same way we did with, I think it was int array bag. when we needed more space, we doubled the size of the array and added things to the end. So I will draw a picture at this point. So let's say here's my array. It has however many slots are going to end up here. 9 slots. I push the numbers 1 through 7 here. The push operation adds things to the rear of the queue. This is the tail end. This is the front end. You can think of queues sort of as pipelines. So if I could actually draw, I'd draw a pipe, and I'd stick a 1 in, it would go as far as it could go. Stick a 2 in, it would go as far as it could go, and so on and so forth. If I pop, one thing I could do is pop this off, cross that out, not use that anymore. Pop this off, cross that out, not using that anymore. If I, let's continue pushing some numbers on here. So we'll push on 8 and 9. Now I've hit the end of my array. So what if I wanted to push the number 10? One option I have is extend my array, which really means copying it to a new array. But eventually, if I keep pushing things on and keep popping things, there's going to be this huge chunk of array at the beginning that's not being used and can never be used again. That's pretty inefficient, especially if I want a program that uses a queue like this to run for a long time. And some of the longest running programs are built around queues. Networking applications all use queues. As things arrive at your computer, they go into a queue until the programs that you're running are ready to use them. It would be really irritating if the routers that run the internet had to be rebooted every couple hours so that we could clear out these queues and build a new one. So instead of doing that, we recognize that instead of extending the array, we recognize that we have 2 open slots here. So why not put 10 here? And if we want to push 11 and 12, we can push 11 on. And now we need somewhere to put 12. Now we have no more space in this array. Now is the appropriate time to create a new array that has enough size. So we would need at least 10 slots. So we might as well build an array of size 20. Copy things into that new array. This is the first part of our queue. So in our new array, we would want 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then empty space. So this ends up going over here, and this ends up I missed. There we go. That ends up going over there. Does that make sense? The book's picture of this is much nicer. They actually have someone who can do graphics. Let's see. That is on page 387. The top of page 387. They have an array called data and an array called bigger array. Same names as they used in IntArray bag in the Insure Capacity method. And it looks more or less like this. But because we're doing things this way, let me backtrack. If we had if we were using a normal array, and every time we popped, we wanted the element that's closest to the front of the array, with the head end, to be the first element in the array, we would have to move every element up one, which would be very inefficient, especially if our queue got massive. It would be very, very time consuming every time we popped an element. We want popping an element to be relatively quick. We want that element now. We're impatient. So that's a benefit to leaving everything in the array exactly where it is and just keeping track of where that first element is. So we can have something like front that points to the front index of the array. In this case, it's 2. And another variable that points to the rear index in the array. In this case, it's 1. And then when we copy things into a new array, we have to change front. Now we get an opportunity to reorder everything and put it in the right order. So front would equal 0, and rear would end up equaling 9. Questions? So do we think we can implement this in code?
So Ryan, could you help me to maximize and reproduce that all these lots in your way?
Yes.
So it's peaceful, right?
Mm-hmm. So really, all that data structures are is an adapter. There are certain things we don't want to deal with that arrays force us to have to deal with, and certain ways we want to interact with data. Since the only basically primitive data structure that we have is an array, we write data structures that are basically an adapter. Software engineering design pattern called an adapter that basically translates from the way we want to deal with data and the way the data actually looks. So we have this data structure in between that allows us to push data on. Once we call push on with a particular element, we don't care how that's stored. This is what I was telling Dion before class started. Separation of responsibilities to the extreme. That is not my job description. I don't care how that happens. This is the queue's job description. It is responsible for figuring out how it's going to store the data. It really doesn't matter to me. I just know that I want to push something on, and at the other end, whatever is consuming the data in this queue, whatever I push onto the queue first should be the first thing that comes off the queue. Whereas with the stack, it's the reverse. Whatever was the last thing to get pushed on the stack is the first thing to get consumed by whatever is consuming the data. Not what I intended to do. So who wants to start us off? Dion, do you want to start us off? Okay. What comes next? I turned off the light. There we go. I'll actually type this part. Array queue. And I'm going to use generics. And I'm not going to concern myself with the clonable interface. The book talks about using the clonable interface. There's a very good reason for using the clonable interface. And that's an idea, a concept called a deep copy. We don't just want to copy a data structure and have all the references that a data structure has to the underlying data stay the same between these two data structures, because then we modify an element in one of the data structures and it ends up modified in both places. By implementing the clonable interface, we can specifically implement a clone method that makes a copy of everything that could possibly be modified by this data structure, and ensures that the copy together, the copy and the original data structure, take up twice as much memory as they originally did. So that if I modify an item in this collection, it doesn't get modified in more places than I'm expecting it to. So, where should I start? I'm not going to worry about constructors first. Should probably worry about instance variables. So, I look at my picture on the board that I can barely see now. I need something to store my data in. Right? And I need something to point to the front and the rear. So there's front, there's rear. What else do I need? I need to be able to interact with this thing. And I mentioned the most important operations are push, pop, peep, and we'll add size as well. We should probably initialize data to something. So I'll take back what I said, and I will implement a constructor. Because of the same issue we run into we run into the same issue we ran into with the generic array bag. Since we're using an array, we need to initialize it with some size. But in this constructor, we actually don't have access to the placeholder or the specific type that the placeholder is replaced with. So we have to create an array of objects. And we ensure in other places in our code that the only thing that can be added to this array of objects is something of type E. Does line 7 look familiar to everybody? Yes? This keyword being used to call another constructor in the same object. So basically, I'm specifying a default size, but I'm calling this other constructor. I can't say I can't call array Q with initial capacity. That's a compiler error. But calling this allows me to call off to another constructor. So now we have something with. Let's make this actually make sense. Rear shouldn't be 0. That doesn't make any sense. No, that does make sense. Don't listen to me. This queue doesn't have anything in it, so the front and the rear should be the same thing. I think that the book does something kind of odd. Hang on. Yeah, the book keeps track of the number of elements in the queue using another variable. So in theory, the circular nature that we're going to apply to this array notwithstanding, the size of the array should be rear minus front. However, there is the possibility, and I think they actually no, they use rear to point to the very last element in the queue. So we'll stay consistent with that. So we'll make that represent the number of items in the queue. Which means that our size method should simply return num items. Let's add things to this array. This queue. The book uses the terms add and remove to refer to putting something into the queue. There's only one place to put things into the queue, and remove to remove things from the queue, and there's only one place to remove things from the queue. I think this is ambiguous. Add and remove kind of implies that you can add and remove from anywhere. The standard terms that are applied to queues are push and pop, just like with stacks. So I will use the terms push and pop. So, bless you. Push. We want to push an E onto this queue. So let's start out by assuming that we don't need to do any error checking. Basically, this is the first element that we're pushing onto this queue. What do we need to do? If there are no items in this queue, that means every array index is open. So we might as well start at the beginning. So if num items is 0, then it's a special case. This is the beginning. Either we've popped everything off, or this is the first thing we're popping onto this queue ever. Set front and rear to 0. And new data goes onto the rear of the queue. And we increment the number of items. What's the other case here? The other case is that rear actually points to a valid item, which means num items is non-zero. The first item, the person at the front of the line about to get their food is at the array index corresponding to front, and the person all the way at the end of the line is at the index corresponding to rear. We don't want to put data in the index pointed to by rear, because now we're replacing the person at the end of the line. They're not going to like that very much. We need to look for the next element in the array. One way to accomplish that is that. And we'll start there. However, if we're wrapping around the end of the array, let's say we have data has 10 elements, so its max index is 9. We've filled the array. We just pushed everything on. We don't have a pop operation, so we can't have popped anything. We've pushed 10 elements on, so rear is 9. We need to wrap around the edge of the array. What's the next available index? The next available index is not 10. Our array only has 10 elements. Its last index is 9. So we need some way of wrapping around. And the book accomplishes this by creating a helper method called nextIndex. And really all this does, see the answer to self-test exercise 17. Sure. What do we want to happen here? If IDX is equal to the current index, we haven't incremented the index yet, is equal to data.length, then we want to return 0. Otherwise, we should return that. No, not quite. I think the book's implementation on page 405 is it's clever. It makes sense, it's right, but it's kind of clever. If IDX is at the end of the array, the last index of the array, it's not going to equal data.length. It's going to be one less than data.length. If it equals data.length, that means that we have already inserted a data point at an index that doesn't exist. That doesn't make any sense. So what the book actually does is increments IDX first to see if that should normally be the next available index. Does that make sense? That should be the next available index. Compares that to data.length. If the next available index, the one off the edge of the array, doesn't exist, it'll equal data.length, and then we can wrap around to the beginning of the array. Otherwise, instead of returning IDX++, we already incremented the index. So just return IDX. Alright, so that takes care of that. The only thing left to do here is make sure that we have enough room for this new element. Which means that if the number of items in this array is equal to the number of spaces we have in the array, we don't have any room. We need to make more room. So if num items equals data.length, we're going to use the same almost the same insure capacity method that we used for the array bag. And we want at least twice as many slots as we actually need. Many items, spot 2 plus 1. That makes sure that if, for whatever reason, I don't have a many items. I have a num items. If for whatever reason num items is 0, it'll still create an array with one slot. So this will still work. So in order for all this to compile, the only thing we need to implement now is insure capacity. Minimum. There we go. So the simplest case is that we already have enough space. If data.length greater than or equal to minimum, return. That was easy. The next option is that the number of items in this array is 0. So we really don't care about preserving the contents of the array we already have. So if num items equals 0. Just set the data array to a new array. And short circuit and return. Those are the easy cases. Now we have two harder cases. One is still on the easier side of harder, and one is closer to the harder side of harder. Our first case is that front is still closer to the front end of the array than rear is. We haven't wrapped around the other side. We don't have to do anything fancy. We just need to take the part of the array that is valid, make this new array bigger so that it fits this old array, and copy the valid elements into the new array. So this is pretty much like the insure capacity from the array bag. We'll use that system.array copy method again. Array copy. It's a lowercase c. And what's this? The sequence of arguments for this? It's source array, source index, destination array, destination index. Ooh. I don't like that. The book decides to keep front at the same thing. So just make a bigger array, move everything down. So front stays exactly the same, rear stays exactly the same. I think I'd rather take the valid data from the old array, move it to the first slots of the new array. Does anyone have a problem with that? Does anyone not understand what the question is? Okay. So I'm going to do exactly that. I'm going to take the number of elements that I have, number of valid elements from the data array from somewhere that's not at the very beginning of the array, move it to the very beginning of the bigger array. So the starting index and the destination array is 0, and the number of items to copy is the number of items that I have. So that'll be num items. And now we can stick bigger array in data, and that's it. Short circuit. Now we only have one other case, and that's the big irritating hard case. This is where the array that we're starting with has a valid part at the end and a valid part at the beginning, some invalid part in the middle. So front is actually greater than rear. We've wrapped around the other element. So we need to do 2 array copies. We need to create a bigger array no matter what. But we need to copy the rightmost piece of the old array into the very first few slots of the new array and copy the first part, the valid part at the beginning of the old array immediately after the end part into the new array. So they use some excellent variable names here. We know we're going to need a bigger array of size minimum. That's a given. Now we need to copy from data from front to the very end of the array. So how many elements is that? That's the length of the array minus front. And I will length, I'll name it something reasonable. Length first part. Length front part equals data.length minus front. And does that make sense? So, given this example, front is 2. Data.length is is 9. There are 9 elements here. 9 minus 2 is 7, and that is the number of elements to copy. So system dot array copy from data, starting at front, copying to bigger array, starting at 0. And the number of elements is length front part. Now we have to copy this part that's at the front. Let's start by filling in the knowns. We're copying from data. We're copying from 0 in data. We're copying to bigger array. We're copying to the first index after the last index that we copied in line 59. We have length front part elements. So those elements went into slots 0 through length front part minus 1. So the next one is length front part minus 1 plus 1, which is length front part. So length front part. And in the book, they call this variable N1. Very descriptive. How many elements do we need to copy? Well, we know it has something to do with rear. But in this case, in the example on the board, the index of rear is 1. That's not going to work. We want to copy 2 elements. So 2 is rear plus 1. And that's exactly what the book has. which they store in another variable n2, but I think that's simple enough that we could just put it right in there. Finally, we need to change front and rear to point to the new front and rear in bigger array. So front obviously is 0. Rear is now pretty much what it's always been, which is 1 fewer than the number of items that we have in this array, which would be num items minus 1. And of course, we need to actually make data point to bigger array. And at that point, we're done with this massive insure capacity method. Are there any questions on that? I'm going to implement a toString method very quickly so that we can actually do some debugging on this. Public string, toString. And just as a refresher, there are 4 rules that apply. Four rules that apply to toString. 1, it is named toString. 2, it returns a string. 3, it takes no arguments. And 4, it does not actually print anything out. So we will start with string. Feel free to use a string builder. It's quote unquote the right way. I'm not too worried about memory though. So. That's probably the first time in a non-contrived example that you've seen multiple initializations and approaches in the same for statement. That is valid and sometimes useful. Empty string means that if I add anything to it, it becomes a string. Which, actually, we should be able to accomplish this by saying data j.toString plus, put some space at the end. And finally return this string. Does that make sense? Cross your fingers, hope it compiles. Sweet. Don't worry if you haven't caught up on that. I'll switch back in a minute. I just want to write a quick main method, aq test, public static void main args. We'll make a simple array queue of integers. My array queue was new array queue. Integers. Let's go ahead and print that out before we do anything with it. Let's make it be identical to the example that's on the board. Okay, so I should have the queue printed out 3 times. I think I'm actually going to change this toString to show me the capacity and how many items are in there. So now everything compiles. I'm going to switch back real quick and run it. Okay, so we start out with an array queue of capacity 9, 0 elements in it. We add 9 elements and we have an array queue of 9 elements of capacity 9 with 9 elements in it. Then we pop something else onto it. We pop that 10. That means that we have to increase the size of the array queue. Since we use that, what is it? The current size times 2 plus 1, we get 9 times 2, which is 18, plus 1 is 19. So our array queue has size 19, and it has 12 items in it when we print it out the 3rd time. Any questions on that? I'm sorry? Print the variables? Yes. So, let's say plus, put a semicolon there, just to make things confusing. Front, rear, and I think that should be sufficient. So compile. Run. So front and rear are 0. Then we add 9 elements. Front is still 0. Front is always going to be 0 because we don't have a pop method yet. And 8, rear is 8 because this is at index 8. And this is at index 11. We have 12 elements, so our last index is 11. And it is break time. In 10 minutes at 3:10 we'll reconvene, or at 3:08 we'll reconvene, and we'll implement a pop method, a peak method, and I think that'll do it. Pop and peak.